So just to recap, the first thing we looked at last lesson was evidence from Geiger and Marsden's experiment on alpha scattering and how that led Rutherford to come up with the nuclear model of the atom. And we also looked at some of the problems with that, including the idea that we needed another force in order to explain how protons can stay together in the nucleus. And that is called the strong nuclear force, sometimes just referred to as the strong force. And that not only holds protons, but also neutrons together in the nucleus. We need to be able to define the terms nuclide, nucleon number, and proton number, and use these to describe a particular nuclide. And then right at the end of the lesson, we went on to look at how light is actually emitted from an atom. We looked in waves at how light came in sort of random bursts, which is why we don't get a lot of interference from light. And this is kind of the explanation of that. So when an electron within an atom is excited by some energy in some way, it can move up an energy level and it will then tend to lose that energy in the form of light as it drops back down again. That light that it emits is, we think of it as like a packet of energy called a photon. So a photon, which higher level students will look at a little bit more in detail, but for everybody else, the photon is, it's neither wave nor particle. It has wave-like properties, so it has a wavelength, it has frequency, but it also has particle-like properties, so we'll actually look at it as having momentum later on. But that's for another day. For now, we just need to realize that actually photons are a form of light that's emitted from an atom when an electron drops down from one energy level to another. And that's really what we're going to look at today. So here's an example of how that kind of works in a model with a football for a nucleus and a tennis ball for an electron. So if a low energy photon of light is absorbed by an electron, basically nothing happens. The energy isn't enough to take it up to the next energy level. But if a slightly higher energy photon is absorbed by an electron, the electron does gain enough energy to jump up to the next energy level, where it's in what we call an excited state and will tend to drop back down. But in order to do that, it needs to release some energy, and it does that in the form of a photon. Now, if a photon with an even higher amount of energy is absorbed by an electron, it can jump up 2 energy levels, and then one of two things could happen. Either it could drop back down to where it started, releasing a photon of the same energy as the one it absorbed, or what it could do is it could drop down in stages, releasing energies appropriate to the energy levels that it drops. So here this is going to drop down to the next energy level, releasing, in this case, a red photon, and then drop down to the very bottom again because it's still in an excited state, and releasing a green photon. So if our electron absorbs too much energy, then it can actually escape from the atom. We call this ionization. So here comes an ultraviolet photon, and our electron has just disappeared completely. It has left the atom. The atom is no longer neutral, it has lost a negative charge, so it is now an ion, so it has been ionized. So when we're dealing with the energies involved in nuclear reactions, although overall the amount of energy released can be very large, each individual reaction is only going to release a small amount of energy. So the unit of a joule is actually too big a unit of energy. So what we need is a unit of energy that's much smaller, and we tend to use the unit of energy called the electron volt. Now, the electron volt is the energy gained by an electron when it's accelerated through a potential difference of 1 volt, and it's used for small energies. Now, I'll explain what that definition means in a second. But basically, 1 electron volt is 1.6 times 10 to the negative 19 joules. So no coincidence, but 1.6 times 10 to the negative 19 is also the charge on an electron in coulombs. So back to the definition of the electron volt. Here we have an electric circuit with a power supply at the bottom and an open gap at the top. if we place an electron on the negative side of the open gap, then it would be repelled by the negative side and then attracted to the positive side. So it would be accelerated across the gap. As it's accelerated, it gains energy. The amount of energy it gains depends on the voltage of the power supply. So if this is a 1 volt power supply accelerating 1 electron, then it would gain 1 electron volt. So what we're going to look at is the wavelengths of photons that are emitted when an electron drops from one energy level to another. So here's the typical energy levels for a particular atom, and you'll see the ground state here is the lowest energy level, and we call that n equals 1. The first excited state we call n equals 2, the second excited state is n equals 3, n equals 4, n equals 5, until we reach ionization, where the electron could escape fully from the atom. Now the ionization level is typically called 0 electron volts, so we base our 0 energy at this point, and so the energies work negatively down to the ground state, which is negative 13.6 electron volts. What that means is an electron in the ground state, if it's given 13.6 electron volts of energy, it will actually be able to escape from the atom completely. However, if it's given a certain amount of energy that takes it up to the first excited state, it will be excited in here and it will tend to drop back down, releasing a photon of energy from there. So your task for each of the following state changes: calculate the energy change in electron volts, the energy change in joules, and the frequency of the photon emitted, and then tell us which ones are visible. So these are the energy changes we're looking at, from n equals 2 to n equals 1, from n equals 3 to n equals 2, and also from n equals 3 down to n equals 1. So I'm going to do the first one for you as an example, and then what I want you to do is do the second two and submit your answers as a photograph to the Google Classroom. So to calculate the wavelength of the photon emitted when an electron drops from one energy level to another, we adopt the following procedure. Okay, so the energy level we're dropping from, n equals 2, the energy is negative 3.4 electron volts, and we're dropping to n equals 1, where the energy is at negative 13.6 electron volts. So in order for the electron to drop from here to here, it must lose the amount of energy that's between these two. So if we subtract one from the other, we get an answer of 10.2 electron volts. Now, in order to calculate the wavelength, we need electron volts into the SI unit of energy, which is the joule, and it's quite straightforward to do this, as long as we just treat the E as being the charge on the electron, which is in your data booklets, and it's equal to 1.6 times 10 to the negative 19, and converting from electron volts to joules, we just stick a joule on the end. So all we've done is replace the E with 1.6 times 10 to the negative 19, which is the charge on the electron, and change the unit to joules. Okay, so that works out that the energy change is 1.63 times 10 to the negative 18 joules. Now we know that the energy of the photon released is equal to Planck's constant times the frequency of the photon. So taking our answer for the energy here, we have 1.63 times 10 to the negative 18 equals, and Planck's constant in your data booklet is 6.63 times 10 to the negative 34 times F. Rearranging that, we get that F is 1.63 times 10 to the negative 18 divided by 6.63 times 10 to the negative 34, which equals 2.46 times 10 to the 15, and because we're working in SI units, we get the SI unit of frequency, which is Hertz. So when the electron drops from n equals 2 to n equals 1, this is the amount of energy that's released in the form of a photon. This is it in joules, and this equation tells us the relationship between the energy in joules of a photon of light and its frequency. So we have a photon of light emitted that's 2.46 times 10 to the 15 Hertz. Now, off the top of our heads, we probably don't know whether that's in visible light or not, in the visible light range. What we do know is that the wavelengths of visible light are from approximately 400 nanometers at the violet end of the spectrum all the way up to about 700 nanometers at the red end of the spectrum. Now, what we need to do is work out what wavelength of light would have this frequency, and we know from our previous topic on waves that c equals f lambda, where, because we're dealing with light, c here is the speed of light, so c equals 3.00 times 10 to the 8 meters per second, and so we can plug in our value for frequency, plug in our value for the speed of light, and we can work out what wavelength this photon would have. So 3.00 times 10 to the 8 equals 2.46 times 10 to the 15 times the wavelength. Rearranging that, we get that the wavelength is 3.00 times 10 to the 8 divided by 2.46 times 10 to the 15, and if you stick that into your calculator, that turns out to be 1.22 times 10 to the negative 7, and again, because we've gone with SI units of Hertz and meters per second, wavelength will have the SI unit of meters. Now, in terms of nanometers, negative 7 to negative 9 for nanometers means we're going to move the decimal point 2 places to the right, so that is 122 nanometers. So, when our electron drops from n equals 2 to n equals 1, it releases a photon that has a wavelength of 122 nanometers. Now, 122 nanometers is not in the range of visible light. In fact, it's a shorter wavelength than violet, so probably be in the ultraviolet range, which would not be visible. So what does this tell us? Well, this is our explanation for the Bohr model, which is based on the evidence of line spectra. So we looked at the spectrum of light, the gas, the emission spectrum, where gases, when they're excited, tend to give out line spectra like this, discrete wavelengths of light. And as we've seen previously, the discrete wavelengths of light correspond to discrete energy levels. So this is actually our evidence that there are energy levels within the electrons in an atom. So different elements will have a different electron energy levels, which means we get a different emission spectrum for each element. So we can actually use the emission spectrum of an element to identify what elements are present in a gas. It's like a fingerprint for the element. And this is actually how we discovered helium on the Sun.